Hey everyone, in this video we're going to talk about the derivative as a function. So in the previous section, we were just talking about the derivative as a rate of change and finding the derivative at a particular point. So the derivative gives us the slope of the tangent line or the instantaneous rate of change at a point. Now we're talking about what about the derivative as a function? So not given a specific point that we want to find a tangent line or the instantaneous velocity. So use the definition of the derivative to find f prime. So this is our notation for the derivative for this particular function. So first thing is remind ourselves what is the definition of the derivative. And our definition is that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So this is the definition that we want to remember. Anything that says use a definition, this is what we're talking about. So let's find the derivative for our function. Now this is a function with a fraction, so we're going to have to do a little work here. So our derivative is the limit as h approaches 0 of f of x plus h. So what is f of x plus h for this function? That means anywhere you see an x, we're going to plug in x plus h. So replace the x with x plus h. Imagine, for example, if I asked you to find f of 2, what would you do? You would replace the x with 2. So this will be 2 over 2 plus 1. So that's the same thing here. F of x plus h, replace the x with x plus h. So it'll be x plus h plus 1. So let's put that in here. So f of x plus h is 2 over x plus h plus 1. And then minus f of x. Well, f of x is our original function, so 2 over x plus 1. And the whole thing divided by h. So the whole thing divided by h. And now we want to be able to simplify this so that we can take the limit. Notice that if I just take the limit right now, plug in 0 for h, I'm going to have 2 over x plus 1 minus the same thing. So I'm going to get 0 over 0, which means do some algebra. Now, I do want to emphasize that in this class where we are right now, we don't have any shortcuts for finding the derivative. So if some of you have taken calculus before, have seen before, whether you took it in high school or you are retaking this course, you may know some shortcuts for taking the derivative, but at this point in time, we have not seen those yet. So anytime you're asked to find the derivative, this is what you're doing, using the definition. So I have 0 over 0, therefore means do some algebra. So what is the algebra that we get to do? Well, we have fractions, so the algebra will be get a common denominator. So find the least common denominator. So looks like x plus h plus 1 and x plus 1, right? Remember, h is another number. So like if h was 1/2, or if h was, let's make it a whole number, if h was 3, for example, this will be x plus 3 plus 1, so x plus 4, and that's x plus 1. So there are different quantities. What I don't want to see is, sometimes what happens is people will add an h on top and bottom to make the denominators the same, but remember, h is a number, so this is a completely different quantity, so you have to multiply. So I'm going to multiply this by x plus 1, top and bottom. And we're going to multiply this by x plus h plus 1. I chose this example because in the previous video series where we did derivatives at a point, I used polynomials and radical functions. So I figure for this one, let's use a rational function. All right, so now we're going to have our same denominator, x plus h plus 1 times x plus 1 minus same denominator, x plus h plus 1, x plus 1. So what are in our numerators? So here I'm going to have 2x plus 2 minus, that's that minus, and then here 2x plus 2h plus 2. I still have this minus, I have not combined it, so I don't change the sign there yet. And I still have the whole thing here is divided by h. If you want to change it so that you don't have a fraction, this big fraction, you can think of this as h over 1 and then multiply by the reciprocal. So I'm going to do that in this next step. So I'm going to have the limit as h goes to 0 and my same denominator, x plus h plus 1 times x plus 1, the common denominator. And now I'm going to combine the numerators, right? Once you have the same denominator, you can subtract, in this case, the numerator. So I'm going to have 2x plus 2 minus, and then I'm bringing this whole thing in. I'm going to use parentheses so I don't forget to distribute the negative. If you're pretty good at distributing the negative as you go, then that's fine. Divided by h over 1 is the same thing as multiplying by 1 over h, the reciprocal. And now let's bring this negative in. If you did it in one step, that's fine. Then you don't need to do this step. Just make sure that you do distribute that negative. So I'll have the limit as h goes to 0. And notice that I still have my limit notation because I have not taken the limit. And if I don't have the limit there, I'm not finding the derivative. I'm just finding the average velocity, average rate of change of the function, but we want the instantaneous. We want the derivative, so we want that limit notation there. So minus 2x minus 2h minus 2. Once I distribute that negative, all over x plus h plus 1, x plus 1 times 1 over h. Combine like terms. My 2x's cancel, plus 2 minus 2, they cancel, so what are we left with? Just a minus 2h in the numerator. So I'll have the limit as h goes to 0 of negative 2h over x plus h plus 1, x plus 1 times 1 over h. So I can multiply that h in. So notice that if I plug in 0, I still have 0 over 0 because of that h there, but I can divide them out. H divided by h is 1, so I'm just left with a negative 2 in that numerator. So I'll have the limit as h goes to 0 of just negative 2 over x plus h plus 1, x plus 1. And remember, our goal when we're doing the difference quotient is to try to get rid of this h in the denominator. And at this point, I'm able to do that. And now when I plug in 0 for h, there's only one h. So plug it in there, I'm going to have, and now I don't need my limit anymore because now I am taking the limit. When you plug in the value that the limit is approaching, you are taking the limit, so I don't need my limit notation anymore. And this will be x plus 0 plus 1, so that's just x plus 1 times x plus 1. And we can rewrite that nicely as minus 2 over x plus 1 quantity squared. And that's our derivative. So that means that for our function, which was 2 over x plus 1, the derivative is negative 2 over x plus 1 squared. So that is how we find a derivative. Now this is the derivative as a function. So what is this helping us find? So this is essentially the derivative. It gives us a formula or a function for finding slope at any point. Slope of the tangent line at any point. And that is the big concept here, that the derivative can help us find slope at any point on the graph. So now say I wanted to find the slope. So find the slope of the tangent line at, let's say, x equals 1. And what about at x equals negative 2? So now, right, at x equals 1, I will say, well, the slope of the tangent is given by the derivative. at the point. So M tangent will be f prime of 1. So I will just take my derivative function and it will be negative 2 over 1 plus 1 squared. So minus 2 over 4 or negative 1 half. And then you do the same thing with what about at x equals negative 2? So the tangent line at x equals negative 2 will have slope, the derivative function, evaluated at negative 2. So what would that look like? I take my derivative function, so minus 2 over x is negative 2, plus 1 squared. So it will just be minus 2. So that gives us, so here we're able to find the slope at any point in the graph. So let's take a look at the graph real quick. So here's my graph of f of x. So let's label it. So this is my f of x equals 2 over x plus 1. So this is the original function. And so what we're doing, now that I have the derivative as a function, this gives me a formula for finding slope of the tangent line at any point. And so we found it for when x equals 1, the slope is negative 1 half. So notice that the slope is negative, so the tangent line should be decreasing, right? So when x is 1, so say that 1 is somewhere over here, so that makes sense. So the tangent line, so if you draw the tangent line, what we found is that the slope here is negative 1 half when x is 1. What about when x was negative 2? When x is negative 2, so say negative 2 is over here, you still have a decreasing tangent line, right? Tangent line with slope negative. This is why I use decimals. I'm not very good at drawing. So our slope here is m equals negative 2. It's just coincidence that when x is negative 2, the slope is negative 2. So I probably should have chosen a different value, but that gives you an idea, right? Actually, this line should be steeper. The slope is in absolute value is larger, so you should have a steeper line. So it's probably not drawn to scale, but this gives us an idea. And notice that even we're going to have lines that are parallel. We can have parallel tangent lines. So let me put the graph here again. So there is a point, there are a couple of points in here somewhere where you could sort that bend in the graph, right? If I draw a tangent line there and a tangent line here, those lines look like they're going to be parallel. So that means same slope. So we have some parallel lines here. So that's another way that having the derivative as a function can help us. So for example, I don't know, what do you think that slope is? Like negative 1 maybe? So one of the questions could be find all values of x where the slope of the tangent line, right, the derivative, is equal to negative 1. So I'm just kind of guessing because those are going down and that the slope might be negative 1. And so what does that mean? So that means I can set my derivative. Well, we know f prime of x, what did we get it to be? Minus 2 over x plus 1 squared. And we want the derivative to be negative 1. So then set the derivative minus 2. Let me do it in steps. Let's set f prime of x equal to negative 1 and solve for x. So that means we're going to set our derivative minus 2 over x plus 1 squared equal to negative 1 and solve. So I'm going to have, how do you solve this? Cross multiply. So I'm going to have minus 2 equals negative 1 times x plus 1 quantity squared. divide both sides by a -1, so I'll have 2 equals just x plus 1 square, and then multiply it out. Or you can take the square root of both sides, but I'm going to multiply it out. So I'm going to have 2 equals, what's that, x squared plus 2x, don't forget about middle terms, plus 1, right? This means x plus 1 times x plus 1. Bring the 2 over, set it equal to 0. So minus 2, so minus 1. So what does this factor? Or does it even factor? Or maybe we need to use the quadratic formula. To check if it factors, we want to see are there two numbers that multiply to -1 and add up to 2? No. So let's use the quadratic formula. So using the quadratic formula, I know x is going to be minus b. So what's a? A is 1, b is 2, c is -1 for the quadratic formula. So negative b, so minus 2 plus or minus the square root of b squared. So 2 squared minus 4ac all over 2a. So probably taking the square root over here would have been much faster. So I'll go back and do that. So if you're thinking, why are you working so hard? It's because I decided to go this way, but I'll show you how to do it, which is the square root. So -2 plus or minus, what is this, 4 minus a minus. So minus and minus becomes plus, so plus 4 all over 2. So that's -2 plus or minus the square root of 8 over 2. And let's reduce that radical. So I'll have -2 plus or minus the square root of 8. 8 is 4 times 2, looking for perfect squares, right? So that means the square root of 4 is 2. So I'll have 2 root 2 all over 2. All right, so then we can reduce. Now here, be careful, right? You don't want to just say, oh, 2 divided by 2 is 1. You can't just reduce this to the first term in the denominator because you're adding and subtracting. Order of operations will tell you first do what's in the numerator and then before you do any division. So here you can factor out the 2. And now we can cancel, right? As long as it's multiplication, we can cancel. But if you have addition or subtraction, you can't cancel that front number. So I have x is equivalent to -1 plus or minus root 2. So that means that this, what we saw in our graph, the two values of x where the slope is -1. So this will be, what did we have? -1 plus root 2. So this is -1 plus root 2. And then so this one must be, minus root 2. -1 minus root 2. And this will be -1 plus root 2 from our answers here, right? Once you separate it. So that means that x is -1 plus root 2 or x is -1 minus root 2. So that's using the quadratic formula. As I mentioned earlier here, probably we may have done better by taking the square root property, solving using the square root property. So if I have 2 equals x plus 1 squared, take the square root of both sides. The one thing that is important here when you're using the square root property is that you are taking the square root of a variable squared. So you're going to get plus or minus, right? Or the absolute value. So this will be x plus 1 and then plus or minus root 2. And then subtract the 1 from both sides. So you get -1 plus or minus the square root of 2, which is the same answer. So we can do that. I wanted to show you something with the quadratic formula in case you don't have like a nice square over here. So those are the values where the x values where the slope of the tangent line equals -1. So having the derivative as a function, it gives us a lot of versatility, things that we can do. We can find when does the function have horizontal tangent lines? What's the slope of a horizontal line? 0, right? So then I will set the derivative equal to 0 to find horizontal tangent lines. In this particular case, I just kind of said like, oh, it looks like based on the graph, it looks like I'm going to have parallel lines. So I just picked a random slope. If I want the slope to be -1, what does that look like? You can find, what if you want the slope to be -2, right? Then there'll be something over here where the slope is -2, and you might have another x value where the slope is -2 as well. So that's another way that we can use our derivative as a function, is to find all kinds of other information about the graph, not just necessarily at one point, but we can get a lot more information from our graph. Right, and then I'll record another video with another example of the derivative as a function.